We're going to skip ahead to chapter 15, and then we're going to come back and do the other ones. Chapter 15 is about chemical equilibrium. So this is a more conceptual chapter, much less math in it. So a chemical equilibrium is usually a dynamic equilibrium. So let's try to explain what we mean by that. In a dynamic equilibrium, we have two opposing processes that are occurring at the same rate. And so one analogy that's helpful is a freeway. Here we see on the right side, cars are going, let's say, north, and on the other side, cars are going south. If the cars are moving at the same rate, then if we looked at the number of cars at the north end and at the south end, the number of cars at each end would be the same, but they are not the same cars. Cars are moving north, cars are moving south at the same rate. So the number of cars really isn't changing, and yet there's a lot of activity going on, right? So there's a lot of movement, and yet the number of cars at each end is the same. So in a chemical equilibrium, what we have is, here's a nice simple example of N2O4 decomposing to form 2NO2. That reaction can occur in the forward direction, but we also can have 2NO2 combining to form N2O4. And so we indicate that with this double arrow, showing that it's going in both directions. So here's the picture up here. We've got these red guys, the N2O4, coming apart to form NO2, but you can also have NO2 combining to form N2O4. If you look at the number of N2O4 molecules on each side, it ends up being the same. It's not changing, and yet they're going back and forth. Does that make sense? It's a little bit, I prefer the airport analogy. Think of a busy airport in the middle of the day. There's people coming in, there's arrivals, people getting off of airplanes. There's people leaving on airplanes, and then there's people coming in and out of the parking lot as well. If you looked at the number of people actually in the airport at, say, 10 a.m. and 2 p.m., the number of people in the airport is probably about the same. Is it all the same people, though? No. A lot of the people have changed. New people have come, old people have left. So there's a lot of change going on. That's the dynamic part. The equilibrium part is that the number stays the same. So equilibrium involves ideas of sameness and consistency. The dynamic is talking about things changing. So we say that a chemical system is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. What is a rate of a chemical reaction? It's a little bit like a rate of speed. How fast is it going? It's a measure of how fast the reaction is proceeding. And one way to measure it is the amount of reactant that turns into product in a given unit of time. We're just going to talk about these in generalities and not in terms of numbers. Reaction rates can be controlled or altered if we understand the factors that influence them. And this is where this has practical application. So what's going on when things react? Collision theory helps us to understand. Collision theory says that a chemical reaction can occur when molecules or atoms collide with each other. Is there a picture coming up? No. So let's just think about this reaction. 2NO2 forming N2O4. In order for this chemical reaction to occur, two NO2 molecules have to come together They can't react unless they come together. If we keep them in separate beakers, they can't react. Even if they're in the same beaker, if they're not running into each other, they can't react. It's a little bit like meeting someone. You're looking for a boyfriend or a significant other. You're not ever going to fall in love and have a relationship if you don't meet the person, right? You have to meet them. Well, meeting them is not always enough. It has to be under the right circumstances. Like if one of you is unconscious after an automobile accident, maybe you met, but there's going to be no chemistry occurring there, right? So collision has to happen. It has to happen with enough energy for the reaction to proceed. When NO2 molecules collide and react to form N2O4, there are bonds that have to be broken and new bonds form. If there's not enough energy in the collision, nothing happens. They just bounce off of each other. Sometimes you meet someone and there's like, there wasn't any energy in the meeting, right? And then maybe 6 months later you meet them again under different circumstances and you fall in love with them. What's the difference? Well, it's the situation. The collision energy is related to particle velocity, and this should make sense. You've got two particles coming. If they're coming real slow, there's not much energy in that collision. If they're coming fast, bang, they hit each other. There's a lot of energy. So higher velocity, higher energy collisions. We've talked about the relationship between the temperature of a gas and the energy, or how fast the gas particles are moving. Gas phase molecules have a wide distribution of velocities. We say there's an average kinetic energy at a particular temperature. But the average is just that, an average. It doesn't mean that all the particles have the same amount of energy. Some have higher energy, some have lower energy. You can say the average income is, I don't know, $50,000 or something. Does that mean everybody earns the same? No, there's people higher, people lower. So in any gas mixture, you have higher energy particles and lower energy particles. So then the collisions also happen with a distribution of energy. Some of the collisions are high energy, some are low energy. High energy collisions lead to products, low energy collisions do not. There's a minimum energy, an activation energy, that has to be met for most reactions. You can think of it as a barrier to the reaction. If you don't have this minimum energy, you can't have a reaction occurring. Many times that activation energy is the energy needed to break bonds in the reactants so that the products can form. The factors that influence the rate of a reaction are the same factors that influence the number of high energy collisions that occur in a given amount of time. So if we have a higher temperature, we're going to have higher energy collisions. Now we've got some pictures. Concentration also affects the rate of a reaction. So the rate of a reaction will generally increase with increasing concentration. So if we look at these three pictures, we've got low concentration, intermediate, and high. In a high concentration situation, these particles, now we're looking at hydrogen and iodine forming hydrogen iodide. So these particles have to run into each other. They're much more likely to run into each other in this crowded condition than they are here. So, if you think about meeting a person of the opposite sex to become interested in, are you going to have better luck in Wyoming or Fresno? Probably in Fresno, because the population is so much more concentrated. You're just going to meet more people. If you want to meet somebody, you don't go out in a field, right? Oh, there's a farmer way at the end. But by the time you get over there, he's left, right? There's just nobody there to run into. If you go to the grocery store, you're going to run into people, maybe literally, but you're going to meet some people. So if the concentrations of the reactants are higher, more collisions. The more collisions you have, the more successful collisions you will have. Temperature affects rate of reaction. The temperature affects the velocity of the particles. So here at a low temperature, these particles are moving slowly. When they do collide, their collisions are lower energy. Down here, we've got molecules running around. They're going to collide more frequently, and when they do collide, their collisions are going to be higher energy. So we're going to have more successful collisions in a high temperature situation than in a low temperature situation. So if we increase the temperature of the reaction, that usually increases the rate due to more collisions and higher energy collisions. So there's a summary. The rate of a reaction will increase as concentrations of reactants increase, generally increases with increasing temperature. So we've got a reaction going on. As the reaction goes on, what happens to the concentrations of the reactants? It decreases because reactants are going to be converted into products. As we convert more and more of the reactants into products, we have less reactant there. The rate is dependent on concentration. As the concentration of reactants goes down, the rate goes down. So, conceptual checkpoint. Chemical reaction between two gases. If we increase the pressure of the gas, what do you think that's going to make happen? Is that going to increase the rate, decrease the rate, or have no effect? Increase. Because when we increase the pressure of a gas, we're pushing the particles closer together, which is essentially increasing the concentration. So increasing the pressure, we expect that would increase the reaction rate. Well, I guess that's a good place to stop.